So first of all, yeah, I'm employed or working at the Technical University of Denmark. It is just 15 kilometers from north from here. So the local speaker here today. From I think also for the next sessions, but anyway, the Technical University of Denmark, it was actually founded by Hans Christian Ørsted. And if you remember him, maybe some of you don't remember, actually it is the person who discovered electromagnetism for just 201 years ago. So of course there was a lot of events organized last year, but everything was cancelled, just like you mentioned this morning, Paula. so I we just try to promote the idea that what will happen, what you don't think will happen if electromagnetism was not discovered, right? I mean, what would be the world like? So just think about it. So actually he has this quotation that the agreement of this law, and now it's not a legal law, but it's a physical law, with nature will be better seen by the repetition of experiments than by a long explanation. And I will come back to that in a little while. Then, yeah, I have been in the university the last, time flies, 29 years. I did my master's in Spain in the University of Complutense of Madrid, and I moved to Oviedo. And in this group was collaborating with DTU, and then they offered me to come to DTU to just exchange 1 year, and then you see what happens. So time flies. Then I started to be involved in some measurement of the magnetic field, and then just what I will tell you about. When I was looking at the other speakers before me, I was thinking, okay, what I would do about my presentation, because in our group, actually, we have delivered flight hardware to more than 100 missions in the last 30 years. So I just can pick up whatever I want, and I wouldn't talk about astrophysics because we have an extreme expert here in the group, or remote sensing because now we have Merayo. Of course, law I don't know anything about. I try to follow it. so I try to put this one first. Now I have seen part of this picture this morning. Then Begoña presented a picture of the sky with the stars. Then I think it was Paula presented the potential event in Norway next year. It was yeah. So for us Spaniards, looking at that, we never seen that in Spain. This nothing happened. These auroras. So for the northern countries, this is more common, especially in the northern Norway and northern Sweden. So can you imagine people in the old days being there and looking at that? This is the art of gods, right? Okay, I tried to take you to a journey about some places in our solar system, because the topic of space instrumentation is used many places, but since we have different experts here, I will try to give you some about space instrumentation on Earth, which is our home, on Mars, on Jupiter, and then I will take you to Psyche. And I hope the journey I'm bringing you is going to be within the regulation laws that Antonino just presented. So, yeah, first of all, let me introduce you to, well, actually, it doesn't have introduction, this one, Perseverance. I mean, now I tell you the citation from Ørsted. I mean, keep going, keep doing experiments, and what the name that the Mars 2020 rover got, Perseverance. Keep going, keep trying, just move on. This is the scientist idea from us to keep going, to trying to investigate, to research, to be thinking out of the box, etc. This is the way that actually this rover is being. So there was a lot of news, hot news in 2020. We were invited to the launch in KFC, but it was cancelled. Not the launch, but the presence of all these VIPs and us, well, the scientists. And then it was landed this year. And this, of course, is not going to be the biggest event this year, because we know that the James Webb Space Telescope is going to be not yet bigger later this year. So the mission lifetime of this rover is about 1 Martian year, which is 2 Earth years. And this is a JPL that basically drives these Mars missions. So From this mission, we have been contributing from the DTU space. Well, actually, basically, to start with, we have a lot of contributions from many places. In this robot, there's actually a Spanish contribution. It's an experiment which is measuring the atmosphere or atmospheric parameters of Mars, wind and temperatures and things like this. It's based on the Centro de Astrobiología in Andalucía. And then there's also contributions from Norway and then Holland. And of course, also from the TU, we have also a contribution. In this case, we are participating in the pixel instrument, the one here, in the robotic arm, which is called, our contribution is the context camera for this experiment. And then the reason of doing that is because, of course, if you know, Perseverance is, the main objective is to try to find out whether we can find life. Of course, we know that we want to see only life in another planet somewhere else. Now, Begoña told us about these exoplanets somewhere else. But then here we have the opportunity to see whether we can in situ determine whether there is life or not. So the experiment that we are participating in consists of a X-ray source, just the one that you are using in the dentist. Just put your teeth and look what is that. And of course, looking at the rest of fossil remains. And then the way it works, we have this X-ray source, and then we have the camera here. Oh, sorry, I just jumped too much. The camera here, that it will, of course, with X-ray, will take some pictures in the X-ray band, and then with the camera, we have take some pictures, and then we are illuminating in different colors, and with different colors, we can determine different structure in the different bands in these pictures. These pictures are about 2 centimeters by 1 centimeter, 3 centimeters by 1, very small ones, and then you can see this is the visible picture. But if you take the picture in different bands, you actually see another structures that will tell you whether there is a remainings of other material, fossils. And the ones of interest is these ones that are the trital parite and silicification, where will tell you whether maybe there was potential life. And this method was developed by a Australian called Abigail Allgood. One paper published this paper is the PI of this instrument, and she's of course working on JPL, but originally she's from Australia because he was investigating, as a geologist, investigating these kind of things in Australia. So now, but the problem is that, what is not life on Mars? Well, sorry. We don't know yet. Or we're trying to see the answer. Actually, also, our instrument is going to find out which of these samples can be collected, and then later on there will be another mission that picks up these samples and brings them to Earth. And here is also another potential problem, because we don't want to bring any alien life into Earth. So this one will happen in space in an extremely secure kind of laboratory before the samples can be analyzed on the ground. So the problem is on Mars. If you look at Mars, if you remind the picture of Mars, that it's a red planet. It's just dry and it's red, right? So the thing is that, of course, because of all the studies also made by remote sensing pictures like the ones that Airbus is doing, there has been missions that have taken a picture of the landscape and then determined that actually there's erosion, and therefore there must be having water and stuff like that. Also, we have measured water on Mars. So why is Mars doesn't have an atmosphere? So they actually the hypothesis at the moment is that at some point Mars had a magnetic field, but because it lost its magnetic field, then all the atmosphere was blown out by the sun. If you think of Earth, here we have a little tiny, of course this is just this is not a scale, as you can imagine. This is 150 million of kilometers. And then we have the Earth here, and then we have the sun, and the sun is just an enormous body that is constantly, is kind of a nuclear reactor, constantly sending particles all the time. What we call it the solar wind. So when we have the Earth here, we have the magnetic field of the Earth, but because of the interaction, if we didn't have the solar wind, the magnetic field of the Earth will be a kind of symmetric structure. Because of the solar wind, it pushes the magnetic field towards the sun side of the Earth, and then and then makes this cavity, which is enormous on the other side of that. So now they may be here that sometimes the sun has some sunspots, some black spots, and in that case, it's like the sun is erupting some clouds of plasma, which is high energetic particles. And these things, I mean, since the sun is not stable, it's constantly doing something, once in a while, we get actually one of these bursts into the Earth. And that makes that actually the magnetic field of the Earth will be trying to protect us from that. It's working as a magnetic shield towards the Earth. If now the magnetic field disappears, then we'll have complete exposure to the actual solar wind, which is not a nice environment for any kind of life. So that's the maybe reason why Mars looks like today as it does, because of that. So in this situation where you have the daily evolution of the sun, you can see that how the Earth reacts, or the magnetic field of the Earth reacts to this constant daily. Of course, we have some daily variations because the alignment of the rotation of the Earth and on the magnetic field are not the same. And then you have also this burst of sun constantly going on. And therefore, you have this structure, and you can see that the sun is, or the magnetic field is protecting us from that. And once in a while, when these effects are extreme, then we call it a magnetic storm. All the particles that are coming here are disturbed, or are sort of the trajectory are changed, so they follow the magnetic field lines of the magnetic field of the Earth. And then they come into these polar areas, and that's actually what is still to the aurora we observe on the northern or southern hemisphere on the Earth. So the magnetic field means something for life. So, but the magnetic field of the Earth has different sources. So the most dominant is the one we observe, which is about 95% of the source of the magnetic field we observe. Is generated in the core of the Earth. It's about 3,000 kilometers of radius. If you imagine the Earth is about 6.2 thousand kilometers in radius, but only half of that is where we have this core where the magnetic field is created. And this magnetic field is about 60 plus minus 60,000 ounces. This is the quantity. I just remember this quantity about. And then today the magnetic field looks like this. I mean, we have, as you see here, we have a larger in the equator. We have about 30, and the direction is horizontal. But on the poles, we say a symmetric type of model. Then we will be coming down on the northern part, and then coming out on the southern part. It's like it's a dipole field, we call it. So, because of this, we want to investigate what happens with the magnetic field, and we know that the magnetic field of the Earth has changed over time. I mean, actually, we call it some inversions of the magnetic field. That suddenly the magnetic field was not like this, but actually the north pole of the north pole of the magnetic field is on the south pole, and vice versa today. But in the old days, there has been actually been swapped, and then this happens once in a while. I actually have records on the continental borders that actually this happens maybe every 100,000 years. So we want to understand why the magnetic field will change shape and also direction. And of course, because this is important for the life on Earth, also make some consequences what will happen in the future. So because of the magnetic field, we are able to actually, it's kind of a, if we may say, X-ray of the internal part of the structure of the magnetic field. We can do it with these observations. So, but in order to do that, we have to first model the large field, and then we have other contributions which are due to other effects. I don't know if this is animation. No, it's not working. Okay, it's fine. Then when we have removed the large contribution of the magnetic field, we have other contributions. We have the magnetosphere, which is due to this cavity that I told you just about before. And then when we can also model that one. Then when we remove that one, then we have some ionosphere currents, which are in a height of about 100 kilometers. And you can see these ones are driven by the sun. Well, You could see it if this was supposed to be moving, but now we take it from this where. And then when we remove these magnetospheric currents, we have the ionospheric currents, and then look at the magnitude. We come back from the previous slide from 60,000 to 61 is 1,000 factor, and then we go to another factor here of 30, and then we remove that because we now understand how this is, and then we take the actual crustal field, which is in the surface of the Earth, which is about of 10 nanoteslas, and then at the end we have also some, because of the moon, the water, the tidal waves are changing, and actually this also creates a magnetic field which is on the order of 2. So we're going from 60,000 to 2 1 nanotesla. How do we do that? We want to measure the magnetic field from the space, and then that's the reason why we want to do this. That because if we have observatories all the way in our planet, then you can see that these observatories, these dots are not well uniformly distributed over the Earth. So if we had a satellite during the day, we have this location over the globe. And then we have this on the night, and then you have the satellite. I mean, you have the Earth that is rotating. You will have an inertial satellite orbiting around the Earth, and whilst the Earth is rotating, this will be scanning completely the magnetic field. This is just in one day. You will have 13 orbits, but in many years, we'll have basically very, very dense coverage of all that. So the observation of the magnetic field started by NASA in the 60s with these missions. It was only scalar, and then they made a vector, MaxSat, and then there was 20 years without any dedicated spacecraft, and then when there was Ørsted, the DTU basically started this project. Then we have scalar and vector, and that's actually what started participation on that one. Then we have the different satellites, CHAMP, Psyche, and today we have SWARM, which is an ESA satellite from the Earth Observation Program, which is dedicated exclusively to measure the magnetic field of the Earth. Consists of 3 satellites in a constellation of about 500 kilometers, 2 of them flying in parallel, and the other one perpendicular in that orbit, such that we can actually make some stereographic measurement of the magnetic field. So we have delivered the main instrument on the spacecraft, which is the vector field magnetometer, which measures the 3 components of the magnetic field, and it measures very precisely, but we need star trackers to tell where the magnetic field is pointing to with respect to a local reference frame located on the Earth. We see that means that if we make a measurement, say that component is pointing north or west or down or whatever, and then also we have built a star tracker system to provide the alignment to this one. The challenge of this star tracker system that was also developed for the previous satellites is that it has to be non-magnetic, because we don't want to measure magnetism for any component of the spacecraft. That's why we have this boom here. Usually, I will show you another picture later. Usually, this boom will be put on the body of the spacecraft, and after launch the boom will release. And this is just one mechanism compared to the James Webb Telescope that will be this peanuts, but it's still very critical. So yeah, we're at a distance of about 3 meters from the spacecraft, and then at the top of the boom we have an absolute magnetometer, which gives us the reference. So just in details how this optical range, this is the optical range covered by thermal shields, because we want to have very stable temperature, because we're measuring very precise, and with the materials we're using are very specifically designed to this purpose, but still have some drifts and so on that we want to control. So this is sitting an optical range that is made out of carbon fiber, very stable, and you can see here that the requirement for the instrument is to measure the range of the magnetic field 65,000 nanoteslas with an accuracy of 0.25 with a pointing accuracy of 1 arcsecond. So what is that? I mean, imagine a golf ball and a distance of 10 kilometers, and then the angle that you will see in this ball actually is 1 arcsecond. So it's very small angles. And if you think of the accuracy that we're talking about here, imagine that you want to measure 1 kilometer with 1 millimeter of accuracy. So this is a quite stringent requirement. So usually what we do is that we get some raw measurements, and we apply this it's the only equation I have here. Hopefully it's very simple. It's just we have the raw measurements. We take the offset, which is a constant, and then we apply some sensitivity. This converts from some units to the actual units of now Tesla, which are physical units, and then we get some rotation with related to the star tracker and to star tracker, and then we get the field components in now Tesla in the right orientation. So we're using GPS, the star tracker, and ASN, this scalar magnetometer, for reference in the time inertial of now Tesla. So we have to calibrate that. I mean, we know that it will work. We are testing a lot of things. We calibrate that, and then we bring it to an astronomical facility. In this case, I mean, since I'm coming from Spain, I travel some contact in Almeria, Calar Observatory, nice place, nice city, actually. And then we go there. But the problem is that, when I say I'm going to Spain to the south, to Almeria, how lucky you are. Yes. The thing is that now I'm showing the picture here during the day, but of course, as you see, it's a star tracker. We need to observe the stars, so we have to do it at night. So yes, we do the installation during the day, and then we do the observations during the night, and then the nights are very long, right? And then when you come back to sleep, then you are very tired. And then usually it's 3 days in a row, because you have to take the night that is available, that is star clear, to make observations. And then we calibrate. We have the optical bench here, and then we have the sensor and the star trackers, and then we establish the orientation, relative orientation between the two systems here. It's a very complex test. So, just as Begoña was saying that, we now, you can see the booms are placed together to the spacecraft here. They are released, the 3 from the launcher. The launcher is the most exciting thing for a lot of, we have to make a big event. And then launch loads, we have to make a lot of work before to ensure that this will work. The temperature, then we have to ensure that it will work at all temperatures. A vacuum, we have to ensure that we don't have, we can get off the read of the heat, or it doesn't get too cold, and so on. EMC, we don't want to get interference. So there's a lot of constraints. Radiation, we're going out of space, and radiation becomes a problem. Radiation is high energetical particles can destroy your electronics. And then SWAM, in this case, is an operation satellite. It has to produce data, so we need to ensure that everything is delivering data all the time. So we try to avoid glitches and things like this. So we have to react very quickly if something happens, to resolve the anomaly if any case happens. So there is a lot of things going on, but system is running today and very good. So we are very happy with the results. So now we're going to Jupiter, because Jupiter has also a magnetic field, if you know. Jupiter is a big planet. And then the thing with Jupiter is that the magnetic field is 20 times larger than on Earth. So that gives us an opportunity to analyze what happens in a larger planet with that. So this mission, Juno, is a NASA mission, also with JPL and Goddard Space Flight Center for the instrument. I will here. We have a large spacecraft. This is a spacecraft that is about 4 tons, launched in 2011, and took 5 years to come all the way to Jupiter. And at the moment, it's operating. We are on the 35 flyby. It's making flybys of the magnetic field of the Jupiter every 40 days. And then here we have large solar panels. And earlier, this is the first spacecraft that went deep space with only solar energy. So that's why these solar panels, early on, it has been some RTGs which uses some nuclear radioactive elements. So this is solely based on solar energy. And then at the top of this bomb, this is about 14 meters of longitude. And then they're also deployed when it's being sent in space. Then we have the boom here, where we have the experiment. Of course, there's all experiments in spacecraft, but I was only talking about the magnetometer. But there's imagers and gravity experiment, and also atmospheric experiments and so on. But in this case, we're sitting there because we want to be also away from the spacecraft, not to be disturbed with that. And then we have the first Perijou one in 2016, and at the moment we're on the 35th, as mentioned. Actually, the last one we passed by also the Ganymede moon in the one of the Galilean moons. So early on, there has been other probes from about Jupiter which came farther away, and from that some constraints on the magnetic field was determined, and this is what we call BIP Model 4. And then you see the first flyby of Juno. Actually, because of the model was developed based on data from that's long away, it's not as detailed as the one from Juno, which suddenly already in the first orbit of flyby, we got a field that it was on the order of 8 Gs that we have never observed such a large field ever before. This is the flyby, with so close we are to the planet here with Juno. Then, based on the first 8 orbits, we make and you can see here also the orbits are more or less equidistant, and then we were able to build a model of the planet that is fairly precise. And then one thing that show up is this peculiar spot here. It's not the red spot, which is atmospheric and winds and so on, as we see in the pictures from Jupiter. This is a magnetic spot. And then if we look into the more in that, what happens here is that you have a magnetic field of Jupiter that is extremely complex. And then based on the observations we have performed is that, because one of the objectives of this experiment, which PI is in Goddard Space Flight Center, is do we have a core, is a solid core or not, like on Earth? And then one of the things that has been discovered is that the dynamo of Jupiter is much closer to the surface than on Earth. But then the other thing that has been found out is that actually we have a field ejecting from the North Pole and coming out in the Southern Pole. But actually we have also some effect here. Actually, it's a 3-pole magnetic field. On Earth we have 2 poles. In Jupiter we have 3 poles, and that's very strange. So it's very complex. So this has been published also in some journal. And then finally, I will take you to Psyche. Psyche is the last object in the solar system of this journey I will bring you to about. This is an asteroid that is in between Mars and Jupiter. So actually going from Mars to Earth, and now to Jupiter, and then back to Psyche. This is a mission that NASA has been planning, and it has been a very one of the problems or one of the challenges with the Psyche is that we have only a window of 6 weeks for launch to arrive in 2026. So the launch is fixed in exactly 1 year from now. And then the arrival will be in 2026. So there is no anticipation for any delays. So people, it has been closed down also at JPL and everywhere else in GTU and so on. So here we have been working very hard to get that. We have just delivered the 2 instruments. This is 2 magnetometers from GTU. This, in addition to a GRNS, this is a gamma ray neutral spectrometer and an imager for Johns Hopkins University and ASU, Arizona State University, which is the PI of the mission. And then we are collaborating with the MIT is actually the PI on the instrument magnetometer. We deliver the hardware, and they are doing the science together with us. So, and the way of the objective of Psyche, it is the name of the asteroid is called Psyche, but also the mission is called Psyche. Is that it's an object of 200 kilometers in diameter, which may be made of metal, maybe actually a missing planet in between Mars and Jupiter. And of course, this will tell us yet more about the origin of the solar system. And then if we discover that, of course, actually, some pictures have been taken by the Hubble telescope saying that maybe it has some composition, but we have to in situ or closer by make a spacecraft or send a spacecraft that actually will investigate even further how Psyche is made of. And that's why we have a magnetometer on board. So the reason why is that if it was to be a planet, of course we'll start with a hot core here, solid core, and then it will have a magnetic field, and then during 4.5 billion years it will solidify, it will be cooled down, and then it will make some more detailed features of the magnetic field, and that's why we want to measure and then find out whether it is a Earth-like core or not. So this is one of the objectives of this mission. So now talking about law again, asteroids. It's an asteroid. We have this in situ reutilization of asteroids and so on. What is it worth? And of course now, of course, this is just of course journalists. They like to say, okay, now we have that object. It's metal. It has some raw materials. How much will it cost? How much can we earn from that? And since from the Hubble Space Telescope they say, well, you have here something like made of iron and nickel, then some say, okay, it could be worth 10,000 quadrillion dollars. And this is what some media publish. That's all. And this, you just have to put zeros. How many zeros is this? Is about? This is about 10 times 10 to the 18th. If you look at the TEMA gross domestic product in 2020, maybe this is the one I could got. This is 0.0, 10 to the 12. You take the Spanish one is 3 times more. You take the US one is about 20 times more. So, but if you look at the zeros, this is 6 orders of magnitude larger than these two. So yeah, I mean, is it worth it to bring it back to Earth? But of course, this doesn't take into account how much effort or how much technology has to be developed to bring it back. But I mean, I just leave it there. This is not my business. Just I wanted to show you that interesting stuff that people is looking in that. And I think that was the last part of my talk.